Hi, this is Dr. Bay, and today we're going to go over an introduction to enols and enolates. Stay tuned.
Organic chemistry,
taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy. Soaring through the sky, try up the thing we fly, give rise to the complexity of life. Living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
For molecules that contain a carbonyl group, Greek letters are used to describe the proximity of each carbon atom to the carbonyl. Notice that the carbonyl carbon itself does not receive a Greek letter. In this molecule, notice that the carbons that are adjacent or next to the carbonyl are labeled as the alpha carbon. 2 bonds away from the carbonyl are beta carbons, followed by gamma, then delta. In the presence of a catalytic amount of an acid or base, a ketone will exist in equilibrium with an enol, and this process is called tautomerization. Recall that tautomers are two rapidly interconverting constitutional isomers that only differ by the position of the proton and the double bond. In the first example, cyclohexanone exists in equilibrium with its tautomeric enol form, and in general, equilibrium typically favors the ketone over the enol. There are some exceptions to this though. In the next example, if we look at this beta diketone, its enol form is actually more stable because of the favorable hydrogen bonding interaction between the hydroxyl proton and the nearby carbonyl group as shown by a red dotted line. This hydrogen bond stabilizes the enol over the diketone. Another exception to this is phenol. The enol is more stable than the ketone because the enol or phenol is aromatic and is much more stable than the ketone because it lacks aromaticity. The mechanism of tautomerization depends on whether the reaction is under acidic or basic conditions. In an acidic catalyzed tautomerization, the carbonyl group is protonated by an acid to form a resonance stabilized cation. Then the cationic intermediate has an alpha hydrogen deprotonated to form the enol. In a base catalyzed tautomerization, the alpha position is deprotonated first by the base to form a resonance stabilized anion, then the O- gets protonated by water to form the enol. Keep in mind that only the alpha protons of an aldehyde or ketone are acidic. When an aldehyde or ketone is treated with a strong base, the alpha position is deprotonated to form a resonance stabilized intermediate called an enolate. Enolates are ambident nucleophiles because they actually have two nucleophilic sites depending on what resonance structure is being used. When the alpha carbon attacks an electrophile, it's called C-attack, but when an oxygen atom attacks an electrophile, it's called O-attack. C-attack is much more common than O-attack, and majority of the enolate reactions that we will be learning about utilize C-attack more than O-attack. Enolates in general are more useful than enols because enolates have a full negative charge and are more reactive than enols are. And also, enolates can actually be isolated and stored for short periods of time in lab, unlike enols. To form an enolate, we have to choose the best base. Depending on the type of carbonyl that's being used, some require a mild base, while others need a very strong, bulky base to form an enolate. Aldehydes and ketones in general will form a mixture of enolates and not react at all if it's treated with a weaker base like NaOH or NaOET. So, if you're using a ketone or aldehyde, they typically need a much stronger base like NaH or LDA, which is a strong bulky base, to form the enolate. However, if you're using a diketone, then a weaker base like NaOH or NaOET is sufficient and can be used to form an enolate, and LDA or NaH are not necessary. Under acid-catalyzed conditions, aldehydes and ketones can undergo halogenation at the alpha position. This reaction can work with Cl2, Br2, and I2, but not F2. The first part of the mechanism starts with the enol formation, where the carbonyl oxygen gets protonated by the acid to form a resonance stabilized intermediate. Then the alpha hydrogen is deprotonated by water to form the enol. In the second part of the mechanism, one of the lone pairs from OH comes down to form a pi bond, while the pi bond of the alkene acts as a nucleophile to attack Br2. Then water deprotonates the extra hydrogen atom to form the alpha halogenated product. So in summary, ketones or aldehydes can tautomerize into an enol, but remember that enolates are much more reactive than enols due to their negative charge. Enolates are ambident nucleophiles because they have two nucleophilic sites, but C-attack is much more common for enolate chemistry. One reaction that utilizes an enolate is alpha halogenation, where a halogen is added to the alpha position of the carbonyl.
Organic.